record. Nice, perfect. So yesterday, in previous video, we saw that if we implement PMOS, and anyhow we have to attach the body to the highest voltage possible. So we figured out that this configuration somewhat looks like this MOSFET is operating in a saturation region, and which means that when the switch is actually supposed to be closed, we will be having a current flowing through it, which is being drawn from CB. So one thing we mentioned that there should be no current being drawn from CB. So it's violating that case, as well as we want this MOSFET to be switched off. So we want no current through it. But it seems like if we use a PMOS to make a switch, then the case comes out to be such a way that there is a current, and this current is given by this formula, which comes from the square law model for MOSFET when it is working in saturation region. So this formula is basically for the current through the MOSFET when it is working in a saturation region, where the VGS is basically given by VG minus VS. So VG is VDD, VS is V in plus VDD. So VGS is basically VG minus VS, which is basically V in. So instead of VGS, we have written V in. So forget about the formula for current as of now, but we don't want any current because we want this switch to be closed. So it's clear that we don't want this as we wanted the battery to hold the voltage VDD without losing it. So we didn't wanted any current to be drawn from this battery. Hence, using a PMOS switch is also not a permissible solution while implementing this last switch. So let's do one thing. Let's visit the NMOS switch again. So we said that if we try to make these two voltages equal using a NMOS switch, and we said that these voltages are either grounded or zero, or tending to or very close to ground or zero. So let's say the voltages are Vx. So if Vx was normally connected to 0 volts, then for the switch, this switch to be on, the gate would have been at 5, right? And if we wanted the switch to be off, then the gate would have been at ground. So but this was for Vx to be 0, but what if Vx is a non-zero value? So let's say Vx is not 0, but it has some value, and let's say Vx is at a voltage of like Vx itself, like it's denoting that it's at some voltage which is Vx. So for the best of operation of this switch, when we want this switch to be on, then the gate of this switch is connected at 5 plus Vx. So when Vx was 0, we said that it is connected to 5. So basically it's 5 plus 0 basically. So when when Vx is not 0, then the gate should be connected to 5 plus Vx in order for the switch to be on properly, and for this switch to behave as off. Like for the switch to be off, the gate should be at Vx, or we can also connect it to ground. We can again get the similar behavior, but ideally, like it to be working as a perfect switch, we want our gate to be at Vx. So then earlier, so now we can implement this concept of Vx. So earlier Vx was 0, and the phi would go. So if we talk about the phi earlier, so we wanted phi at gate, right? So what is phi? So phi was basically going from 0 to VDD, from VDD to 0. So that was it when Vx was 0, but now Vx is some kind of value. So what we say that we had the phi as 0 and VDD in track phase and in hold phase. But now instead of 0, we have some voltage Vx. So in order to maintain the same difference, we have the upper voltage as VDD plus Vx, because the upper voltage was the phi was going from 0 to VDD. Now it goes from Vx to VDD plus Vx. So that's how we maintain the same behavior of the NMOS switch. So now we can say that instead of having phi 2 over here, we must have phi 2 plus VDD in order to implement a NMOS switch instead of a PMOS switch over here. So we had VDD over here, right? So instead of having Vx, so we can realize this Vx as any value, like it is a voltage, right? So we can realize this Vx as VDD also. So if we realize it in that way, then we can implement a NMOS here as well. And But for implementing this NMOS over here, we need to provide phi 2 plus VDD instead of just phi to the gate. So how do we generate? So this is how we implement NMOS over here to get rid of the uh, unpermissibility of PMOS. So instead of using a PMOS, which is not permissible, we can use a NMOS and fix the problem. But then what we need is, instead of phi 2, now we need phi 2 plus VDD. So how do we generate phi 2 plus VDD? So phi 2 is basically a phase. So like either a track phase or a hold phase. So how do we generate a phase itself and a VDD in addition with it? So again, let's suppose, so we have a clock phi, and that clock goes from 0 to VDD to 0 to VDD in our case. But it's like, let's say we have a clock with phi. So now what do we want? We don't want phi. We want phi plus VDD. So we want this clock to go from 0 to phi plus VDD instead of 0 to phi. So then to implement this, we again come back to the concept where we say that if we would have had a battery whose value was VDD, then if we, at this point, if we have phi and we attach it to a battery VDD, then at this point, we will get phi plus VDD. So this was, now this sorts out our problem, right? So how do we implement a battery? So again, in order to generate phi plus VDD, um, what do we do is we implement the battery and we say a capacitor is as good as a battery when it is charged at VDD. So we want the value of our battery or the voltage of our battery to be VDD. So if we charge this capacitor to add to the value of VDD, and we don't draw any current from this capacitor, then it is as equal as battery with the value VDD. So again, we have phi just the way we had here. Then we have a battery just the way we had here. So at this point, we will get phi plus VDD. So, but so at this point, if we want to get phi plus VDD, we need to charge this capacitor with VDD. So that's why we need a switch. So why do we need a switch over here? So at this point, if we want phi plus VDD, so phi will go from hold phase to track phase, right? So when phi will go from hold phase to track phase, so in this manner, so in track phase we need phi plus VDD, and in hold phase this capacitor is sitting idle, so we can charge it with VDD again and refresh it. So we have seen this concept already. So that's why we need a switch over here. And let's say if we need a switch over here, and again, so basically in order to generate phi plus VDD, we again need a switch, and that switch needs to be operated with phi bar plus VDD. So again, we are revolving around the same problem. So hence, in order to generate phi plus VDD, we come around a situation where we now need phi bar plus VDD. So what can we do? So basically, we had our phi, right? And we needed phi plus VDD. So when phi is 0, this switch, so what we were expecting was phi plus VDD. In order to get phi plus VDD, we added a battery of value VDD along with phi. So let's say this is the implementation. So when phi is 0, so when phi is 0, the switch must be closed, right? So like when phi is 0 in hold stage, the capacitor should be charged with VDD. So when phi is 0, this switch must be closed. Means if we are implementing a NMOS over here again, so in order to close this switch, it must be controlled by phi bar. So it must be controlled by phi bar. But again, the switch needs to be equalized these two nodes with the voltage VDD. Hence, it needs phi bar plus VDD at its gate in order to switch off. So not in order to switch on. So in order to generate phi plus VDD, at this gate, we need phi bar plus VDD. And then we can also say, we can also, like, for example, in order to generate phi plus VDD, we need phi bar plus VDD at the gate. And we can also say that to vice versa, we can say that to generate phi bar plus VDD, we will need phi plus VDD at this gate. So basically, when we look at these two circuits, so basically this circuits gives us phi plus VDD, which we wanted, but it needs phi bar plus VDD. So basically it needs something from phi bar. This circuit has has the potential to give us phi bar plus VDD, which this circuit needs, but then it needs something which is related to phi, which is phi plus VDD, which this circuit is capable to give. So these two are interdependent on each other to work, right? So let's assume that we club this both together, and when we club these two together and when we implemented these switches using NMOSes, so we have our NMOSes over here, and from this point we are getting our outputs. So basically we are getting our outputs from these points, and these are the NMOSes applied. This is the VDD. So this is the VDD, and basically we have a capacitor, and the lower plate of a capacitor is exposed to phi and phi bar. So that's how we implement it, and we have phi. So to generate phi bar, we just use a inverter. So when we implement this kind of a structure by clubbing these two circuits, so basically when our phi, so phi is a cycle, right? So we have phi as a clock or as a cycle. So when phi is 0, what happens? This inverter inverts and provides us with phi bar. So the absolute value of phi to be 0 means it's at 0 voltage, and absolute value of phi bar will be basically VDD. So if phi bar is VDD at this point, then this point will be VDD. And if this point is 0, then again this point will be again also 0. So when this point is 0, this point is VDD. So then this VDD is provided to the gate of this NMOS. And if VDD is provided to the gate of this NMOS, the drain of this NMOS has VDD from here itself. So we have drain at VDD, we have gate at VDD. So then its source, or basically this terminal, will become VDD minus VT. So that's how it will, this terminal or this node will change from 0 to VDD minus VT. And now, hence when gate of M1 is at VDD, so eventually its source, so basically it will go from 0 to VDD minus VT. So when it goes to VDD minus VT, now what happens when when the phase goes from hold to a track phase? So when it goes from 0 to VDD, so this 0 basically, now the state of phi has changed from 0 to VDD, right? So it was 0, now it has changed to VDD. So then when the state changes, so now the phi has the absolute value of voltage VDD. So if it has VDD, then phi bar will be 0. When phi bar will be 0, so basically if it has VDD, so it will push this VDD to this capacitor. And now at this point we already had VDD minus VT. So in addition to this VDD minus VT, now this VDD will get add up, and this point will be at a voltage 2 VDD minus VT. So this 2 VDD minus VT again will be supplied to the gate of M2, and if the gate of M2 is at 2 VDD minus VT, the drain is at VDD, so then this point or the source will go from 0, or basically it will go to VDD. So when it will be at VDD, this capacitor will be charged to VDD, and when it will be charged to VDD, this VDD goes to the gate of this MOSFET. So now the gate of this M1 had already VDD. Now when more contribution of VDD goes here, and it becomes 2 VDD. So now if the gate is at 2 VDD, if the drain is at VDD, so its source goes from 2 VDD minus VT to just VDD. So that's how the charge or the voltage across this capacitor becomes VDD. So once we run this circuit for a couple of cycles, both the capacitors get charged to a value VDD. And once both capacitors get charged to VDD, so basically that's what we wanted, right? We wanted this capacitor at VDD. So if we have phi over here, so at this point, basically we will get, so basically at this point, we will get phi plus VDD. So in order to get phi plus the voltage VDD at this point, we run this circuit for a few cycles, and after a couple of cycles, both capacitors get charged to VDD, and we can arrive at this stage, and we can easily get these two components which we already wanted. So at this node, we will be having basically, this is what we have over here, right? So at this node, we have phi plus VDD, and at this node, we have phi bar plus VDD. So both things we have, and now we have implemented this using MOSFETs. So now we have the factor phi plus VDD, and we can apply this to the gate which we wanted over here. So now we have phi plus VDD. So phi 2 is basically a phi. So we have a phase plus VDD, and we can apply at the gate. So now all our switches are basically applied with using MOSFETs, either NMOSs or PMOSs or transition switches. So basically this structure is called a Nakagome charge pump, and once both capacitors are charged to VDD, the loop has, so there is a loop over here, and this loop has no effect, or it is sitting ideal in our circuit, whole circuit, or we can just think of them as batteries which are holding VDDs. So now one last thing. So now that we have implemented all the switches in our sampling circuit with MOSFETs, so now our circuit is ready. So one last thing we need to make this whole circuit work is we want to make sure that, so basically we had our own circuit, right? So we had this kind of circuit, right? So we have implemented all the switches, and we just looked about this switch. how to implement this complicated switch. But now we have implemented this switch using NMOS as well. But now what we need is we have to take care that during phi 1 our phi 2 should be not overlapping, or phi 2 should be open when phi 1 is closed. And when phi 2 is closed, so this is how phi 2 is closed, right? Our phi 1 should be open. So phi 1 and phi 2 are two clocks or two uh, phases. So they should not overlap. They should be separated out. So then um, phi 1 and phi 2 must not overlap. And even though we say that like our job is to design the circuit or the chip, and we will be provided with the clock externally, but even though if we are provided with a clock externally, we need to what we need to do actually is to take that clock, and internally we have to generate two non-overlapping clocks, because we need two clocks if we talk about two different phases. So we need two different clocks. So we are provided with one clock itself. So this is the clock we are provided with, but internally we have to generate two non-overlapping clocks, and these two clocks should not overlap, as we looked at the reason why. So we will analyze the core of a asynchronous circuit to produce or to generate two non-overlapping clocks. So we have a SR or RS latch, and this latch is made with a NAND gate. So we have our clock like this, and we have two NAND gates arranged in this format. So this is a RS latch, and let's assume that the inverter, so the inverter present here is delay free. So there is no delay introduced by this inverter itself. But the two NAND gates, these and this NAND gates, so they have the delays, which is TD, and that delay is deliberately made large. So why do we need that delay, or why it is purposely made large? So because we need to have the control over the non-overlap time between phi 1 and phi 2. So we'll see it soon when we need that time delay, because basically this time delay parameter TD allows us to control the amount of dead time between phi 1 and phi 2. So basically when we go from phi 1 to phi 2, ideally we can say that, yeah, like we switch from phi 1 to phi 2. So basically it's a direct switch. So but ideally when we implement it, so we have a RC times constant, so we will get some spikes. So we need to have a buffer for that to die out, because we don't want these two phases to overlap or to interrelate between each other. So that's why to control the amount of dead time between phase 1 and phase 2, we need this time parameter TD. So we'll see it soon.